Today we're going to talk about how to, as it says in the title, manipulate a series. Now, we talked last class about Taylor series. We talked about the different ways to create them. And now we're going to actually talk about how to add, subtract, multiply, divide, and even take the derivative or the antiderivative of a series. Okay? Now, since most series are based on polynomial equations, we're going to be using the power rule a lot. Okay? So, as you can see here, we have a function f of x that is a sub n, which is the pattern, x minus c to the n. They wrote it out. This is a power series with a radius of convergent r and an interval of convergence from c minus r to c plus r. So its derivative, you treat the a sub n as a constant. You bring the power down, n times a, and the power drops to n minus 1, just like regular power rule does. Does that make sense to you? Because that n is going to be a number. And anytime n is a number, you just always bring the number down and drop it by 1 when you take the derivative, which creates a new series. And then the antiderivative happens to be you raise the power by 1 and then put it under 1 over n plus 1. But notice where the c is. The c is on the front, because usually when you write a series, the constant is in the front. The constant's first. So usually when we did antiderivatives, we wrote bloody, 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 blah plus c. Now we put the c in the front. Okay, only difference. Now, this is huge, because when I did this the first time, I did it the long way, and I'm about to show you the short way. I'm so glad I noticed this. It says the radius of convergence, which is capital R, of the series generated by differentiating, taking the derivative, or integrating, is the same as that of the original. So in other words, as soon as you do it for the original equation, those two numbers at the end of the interval are the same for the derivative and for the integral. However, the interval of convergence may differ at the endpoints. So once you do the derivative, you don't have to do the ratio test and figure out what the two numbers are, because they're already there. You've already found them. You just have to test the two endpoints to see if they're still convergent or divergent. So, for example, on the original problem, it may diverge at one endpoint, but then it converges on a derivative. It varies, and we'll do a sample problem to talk about that. So here is our Taylor polynomial right here, x over 2 to the n. Find the derivative and the antiderivative and the interval of convergence for all three power series. Okay, since we already know the function for this, let's use this one to find r and the interval of convergence for the original equation. So let's move this up. So using this function right here, what test do we want to use to test for convergence?
Root test.
I would say the root test is a good choice. So we're going to do the root test here underneath this problem. Kind of try to keep all this stuff in the left-hand column, because we're going to have a column for the original, column for the derivative, column for the antiderivative. So the root test would be the limit as n approaches infinity, absolute value of this function, x over 2 to the n, and then a 1 over n outside the absolute value. How do we clean this up?
X over 2.
The n's are going to cancel, which means the limit goes away also. Okay? So all we're left with is x over 2. That's it. Now, in order for root test to converge, what does this have to be? Greater than 1 or less than 1?
Less than 1.
It has to be less than 1 in order to converge. So now we need to do what we've done for the last two classes. We need to take the absolute value bars off and simplify, get the x by itself. How do we write it without absolute value?
Take out the bars and put it
What do we put on the front?
-1.
Negative 1 is less than x over 2 is less than 1. Now what? Multiply by 2 on both sides. So that would be negative 2 is less than x is less than 2. There's our interval. Okay? We don't know what happens at the endpoints yet, but this interval, which I'm going to box in, is the same interval for all three problems. The function, the derivative, and the antiderivative. Okay? So I'm going to come over here. I'm going to write negative 2 to 2. Do not put brackets or parentheses, because I don't know yet which one it gets. Put the two numbers down and let's test the endpoints. This is what we did last class. So we're going to test x equals negative 2 first. How do we test it? We go back to the original problem. We plug -2 in for x and see what happens. This will be -2 over 2 to the nth power, which reduces to what? -1 to the n. Now, after we've done this a couple times, you're going to see the same kinds of things happen over and over again. We're going to write it out the long way now, and then eventually we're going to just know. Okay? How does this pattern go?
It diverges. It oscillates.
It goes back and forth, -1 plus 1, -1 plus 1. This one actually starts with +1. It really doesn't matter which one you write first, and then it goes -1 plus 1, -1, and so on. And this one is going to oscillate, therefore it diverges. Okay? It oscillates, therefore it diverges. So what does -2 get? A parentheses or a bracket?
Bracket. Parentheses. I mean parentheses.
Parentheses. So we put a parentheses on the -2. Okay? X equals +2 now. So that's going to be +2 over 2 to the n, which is 1 to the n. 1 plus 1 plus 1 plus 1, and so on. Is that sum approaching infinity, or is that sum approaching another number?
Infinity.
It's infinity. This is approaching infinity. This one is diverging. So its endpoint also gets a parentheses. So there is my interval of convergence right here, -2 to 2, for the original equation, in parentheses on both ends. Okay? That's for F. Are we good?
Don't we define R?
Pardon me?
We don't define R.
Oh, we didn't talk about R. No, all it asks for the interval of convergence. What is R going to be, by the way?
-1. 1/2.
Careful. What is 2 minus -2? 4 divided by 2 is 2. R is 2. I'll go ahead and write that down. R equals 2. All right, any questions? Are we good? All right, let's go ahead and do the first part of the derivative. So, f prime of x equals, okay? This is a power rule problem. So what happens to the n when I take the derivative? Where does it go? In the front, right? So this is going to be, first of all, oops, we got to write sigma. N equals 0 to infinity of n times x over 2 to the what power?
To the n minus 1.
N minus 1. Now, I don't know if you realize this. This is chain rule. You have an outer function, which is the power of n, and the inner function, the x over 2. Okay? Now that I've taken the derivative of the outer, what is the derivative of the inner? Okay, what number is in front of the x?
Oh, it's 1/2.
It's a 1. It's 1x over 2, which is the same as 1/2 x. So what's the derivative of 1/2 x? 1/2. So it's times 1/2. You see that? Okay, so now we're going to write it in a little more formal way, which makes it easier to find the other stuff. So we're going to write sigma again, n equals 0 to infinity, bring the 1/2 over, n over 2, x over 2 to the n minus 1. All right, now that we finished the derivative, I want to remind you that the interval of convergence is the same for the derivative as it was for the original equation. So we're going to go ahead and just write the -2 comma 2 without its brackets or parentheses. All we have to do is test the endpoints. We don't have to do all this roots test stuff again. Okay? So when we do x equals -2 here, we're doing it to this one that we just cleaned up. So that's going to be n over 2 times -2 over 2, which is -1 to the n minus 1. So this time we have a little bit more than just a -1 or a 1. We have an n over 2 to contend with. So when it comes to doing the process from here, you may want to write out a few terms to kind of see what's happening. The -1 is going to do what to the problem, to the series? It's going to make it alternate, yes. So if we plug in 0 to start with, that's going to be 0 over 2, which is 0. So the first term is 0. And then 1 over 2, But is it the 1/2 going to be negative or positive? If I plug in a 1 right here, it's going to be positive. So positive 1/2, and then the next term's negative 2 over 2. The only thing that's changing is the top, because that's where the n is. The next one is plus what? 3 over 2, right? And so on. Are those numbers getting bigger or smaller? Bigger. So this is an alternating series, but if I took the limit as n approaches infinity, is it going to 0? No, it's going to infinity, so it is a diverging situation. So I'm going to put a parentheses on the negative 2. All right, now same process with the positive 2. So that'd be n over 2 times positive 2 over 2, which is positive 1 to the n, minus 1. Whoops, forgot the minus 1. Okay, so the 1 doesn't really do anything, because 1 to any power is 1. So it's just the n over 2 I'm really worried about. So that's 0 over 2 plus 1 over 2 plus 2 over 2 plus 3 over 2 dot, 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 dot. Converge or diverge? That's diverging because it's getting bigger, isn't it? Each term is getting bigger. So that is a diverge. So once again, that's both parentheses. Now, is that going to happen every time? Not necessarily. Maybe, but not for sure. All right. Questions to this point? I gotta scoot it over. I'm running out of room. There we go.
Is that a 0 in the beginning?
Yes. Didn't close off the top. Yes, ma'am.
Did you just use the same integral convergence in the first part with the negative 2, comma 2?
No, I use the numbers are the same, yes.
Yeah, that's...
But the endpoints, you don't know whether the bracket or parentheses, and they will be the same every time. Okay, time to do the integral, the antiderivative of f of x dx. Okay, remember it's going to be c plus, because the c goes on the front, summation n equals 0 to infinity. Now, remember, don't make the same mistake I did. When I first did this, I tried to go back and take the antiderivative of this one. No, that's the derivative. I don't want to take the antiderivative of the derivative. I want to go back to the original equation right here. Okay? So, when you do, before we write anything, what's the antiderivative of x squared? 1/3 x to the third. So the power goes up, right? And we have something in front of it. So we're going to move this over. We're going to do x over 2 to the next higher power, which is n plus 1. And then we have 1 over n plus 1 in the front, right? 1/3 x to the third is kind of what we're talking about. But there's one more thing we need. Does anybody know what it is? Okay. If I were to take the derivative of this to check it, the n plus 1s would cancel. This power would drop back down to n, but what else would pop up? A 1/2. I don't want a 1/2. How do I counteract a 1/2 I don't want? I give it a 2. So I'm going to turn the top of that into a 2. You got to just play with it a little bit. Yes?
Are you saying that you would do that in order to just have x? Have x?
Yeah, I want it to be back to the original equation over here.
Oh, so what's the point of giving it the 2 then? Like.
Okay, so let me do it one more time. If I took the derivative of my answer, I should be back to the original. The n plus 1s will cancel. This will come back, and this will drop to an n. But then when I take the inner derivative, I get a 1/2. I don't want a 1/2, so I need the 2 to balance it out. Okay? All right. So, there we are. There's no real cleanup to be done. Yes, ma'am. Question?
I was wondering, what about the C?
C's right there. We're not going to find C at this point.
There's another one in the sigmas, a n to x minus c.
Okay, in this case, the original problem didn't have a C. Remember when we did these the other day? C was 0 if there was no parentheses. C is 0 for all of these. So we don't need it. That's a good point. Thank you. That's a different C. This C in the parentheses here. Can you see what I'm pointing at? Nope. This C right here is not the same as this C right here. One's capital, one's lowercase, so two different things. This is the center. This is the constant at the end of an integral. Okay? Don't get them confused. All right, now we're ready to do -2 to 2 again. This time one of them is going to converge, maybe both. I'm telling you right now. X equals -2. That's going in for x. So we're going to have 2 over n plus 1. And then -2 over 2 is -1 to the n plus 1. Okay. I think I'm going to write that out a little bit. So it's starting at 0. 2 over 1 is 2. And this is going to make it a positive or negative. Let's see. 0 plus 1 is 1. So -1 to the first is a negative. So that's -2 really. First term is -2. So if the first one's negative, second one's positive, and that's 2 over 1. No, yes. Now it's going to be 2 over 2. Remember that the -1 is just making it oscillate. So we'll have -2 over 3 plus 2 over 4 and so on. Okay, just take a look at the numbers as they are. Are they getting smaller? Yes. So there's a possibility it's going to converge. So what test do we use on this situation? What kind of series is it? Alternating. Okay, alternating, two things have to be true. The limit as n approaches infinity of the function has to be 0. Now remember that the function of actually, let me change this now that I wrote that. I want to put the 2 over n plus 1 right there. That's what belongs there. This should be 2 over n plus 1 because we don't worry about the -1 to the n. Is that limit 0? Yes. And it's supposed to be. What is the second thing that has to happen in order for it to converge? Say it one more time. The terms are decreasing. Exactly. Are these terms getting smaller? Yes. So write a sub n plus 1 is less than a sub n. Therefore, this one converges by the alternating series test. And yes, you can abbreviate. So this one gets a bracket. First bracket of the day. Okay. I'm going to stop for a second. I want you to try the +2. See if you can figure out what it's going to do. What kind of series is this? Say it louder, you're right.
Harmonic.
It's harmonic. Y'all see the harmonicness of it? Take the tops off. It's 2 times the harmonic series. Since it is harmonic, it diverges. Therefore, it diverges. So that one gets a parentheses. Any questions so far? Okay. That right there is about half of what you're going to need to understand how to do today, how to take the derivative and antiderivative, and then find those radii of convergence. The rest of it is going to involve the page that we put into your flip chart. So you may want to get your flip chart art out and open it up to that last page. And if you turn your notes to the next page, you will notice that that chart is on the next page of your notes. Okay? Now, I just took this chart and put it into your flip book so you're not having to flip through your notes constantly. You're going to be referring back to this quite a bit. These are the common Taylor series, for different functions of x. Sine, cosine, e to the x, and 1 plus x are the most commonly used. Now, when I've looked at some BC questions, I've seen them say, given that sine x's polynomial is blah, 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 do this to it. Sometimes they'll give it to you. Sometimes they'll have you generate it. But what we're going to do is we're going to take these and we're going to change the x to possibly 1/2 x or x plus 5. And we're going to see how does it change that nth term? How does it make the series change a little bit? It still has a pattern, but it's not the same one. So put a check mark by the first 4. If you can memorize those, it's awesome, but we're not going to make you memorize them. You can always derive them yourself anytime you need them. But for the work that we're doing today, if you keep your flip chart handy, whatever problem they give you, you pull off the chart which one they give you, and then you just modify it. is what we're doing, okay? We're not going to do number 2 right now. We're going to do that next class. So if you would now flip to the next page at the top, and we're going to work on this page right here, and that is generating variations on a power series, okay? So look at number 3. It says generate a power series for sine of 1/2 x centered at 0, including the general term. That's the nth term. Mark out the in 2 different ways. We're not going to do it 2 different ways. We're going to do it just one. Okay? So, take your flip book and copy down what sine's pattern is. So, sine of x equals, it is x minus x to the 3rd over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial plus dot 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 plus negative 1 to the n, x to the 2n plus 1 over 2n plus 1 factorial plus dot dot dot. Okay. That is the Taylor series that we're going to modify. This is an easy algebraic process. What's going to be the tricky part is coming up with what the new nth term is. Okay? So now underneath here I want you to write sine parentheses 1/2 x equals. What I want you to do is on the terms that we wrote out, change every x to 1/2 x. So this x becomes 1/2 x minus, now we have 1/2 x to the 3rd over 3 factorial plus 1/2 x in parentheses to the 5th over 5 factorial. Are you seeing what I'm doing? I'm just substituting in the 1/2 x. Okay, I want you to go to just that far. Try not to write the nth term just yet, because it's going to change too. So what we need to do now is clean this up so we can see what the new pattern is. Bless you. So 1 over 1/2 x minus. If you're raising numbers to powers, just leave them as powers, okay? Now, because this is a 1/2, that 2 to the 3rd really goes where? Do you understand my question? 1/2 to the 3rd is 1/8, right? So it's like a 1 on top and an 8 on the bottom. The 8 is with the 3 factorial. But we're going to leave it as a fraction. So we're going to have 1 over 2 to the 3rd times 3 factorial, and then x to the 3rd out to the side. I like the numbers as a coefficient in the front. Okay. Now, how is the next term going to look? 1 over what? 2 to the 5th, 5 factorial, and then out to the side, x to the 5th. You seeing the pattern? And let's do one more. So the 1 to the 7th is just 1. We don't worry about the 1. So it's going to be 1 on top only, and then 2 to the 7th, 7 factorial, and then x to the 7th out to the side. Well, I'm glad I caught that. Plus dot dot dot. Do all of you see what I've done? All right, let's see what's going on. So let's draw our fraction bar to draw our nth term now. So, first thing, is it alternating?
Yeah.
Yes. So we need a -1 to the n power, maybe n plus 1. Let's figure out what it is. Now, does this series, what n gives me the first term? 0? If I plug in 0, does that give me the first term? Let's try it. -1 to the 0 is positive 1. Oh, that sounds right. If I put a 0 in here, that's x to the positive 1. Yeah. And then 1 factorial. So the 0 is the first term. So if I plug a 0 in here, is that going to give me a positive answer? Yes. Okay. Now, let's not worry about the x's yet. Let's worry about the denominators. Look at the 2's. The exponents go 1, 3, 5, 7. How much are they adding every time to the exponents? 2. Now yesterday when we started class, we talked about what to do when the pattern is adding 2. It's a base of 2 with a power of 2n. Why 2n? Because I'm adding 2 every time. How do I adjust that? 2n minus 1 plus 1 minus 3. What should I do so that I get a 1 here? By plugging in a 0. Should this be 2n plus 1? If I plug a 0 in here, that's going to give me 2 to the first, and that's what I want. Okay, you see it? Okay. Now the denominator, excuse me, the factorial number is the same as the exponent. Agreed? So the factorial is 2n plus 1 factorial. The exponent on 2 and the factorial are the same. Now, I'm going to go ahead and put the x on top just because I've got this nice long fraction bar. What should x's power be? Just 2n? 2n plus 1, same as the factorial. Any numbers that match, make sure you give them the same n. Okay? Plus dot dot dot, done. That's what I'm looking for. Okay, let's jump down and do another one. Move that out of the way. Let's do number 4. Okay, this one says cosine. So take your chart and copy the cosine one down. I don't remember what it is. I have to look. So it's going to be 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial plus dot dot dot. I'm out. I don't have as much room. I really don't need the nth term. So how is this going to look? Well, we're going to put the square root of 2x where all the x's are. So that's going to be f of x equals, this is cosine of x. I didn't make it clear that that's cosine. That's not what that equals. So it's going to be 1 plus the square root of 2x squared over 2 factorial plus the square root of 2x to the 4th over 4 factorial minus the square root of 2x to the 6th over 6 factorial plus dot dot dot. Notice what's in the parentheses with cosine. Square root of 2x. The one that we were given on the flip chart is cosine of x. So I'm taking all the x's and I'm replacing them with the square root of 2x.
So for the next one, where it says sine x cubed, and then in the function thing, where the first x is, we would put x cubed.
Yes.
And then the second one we would put x cubed, and then outside one parentheses x.
Yes. 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 Exactly. Ma'am.
Is there supposed to be a negative after the 1 instead of a positive after that?
What do the rest of you think?
It's supposed to be negative.
It is supposed to be negative. Good catch. Jocelyn's awake. So there should be a minus right there. Okay. Clean it up. Moving on. 1 minus. What is the square root of 2x squared? 2x. Over 2 factorial plus. What is the square root of 2x to the 4th power?
2x squared.
Careful. Almost. 4x squared. You got to square the 2 also.
Oh, you're on it.
Okay? Now what about the next one? Oops, it's a minus again. Boy. It's 2x times 2x times 2x, which is, that's too big of a height. No, just 3 of them. 8 to the 3rd over 6 factorial. Plus dot dot dot. Now, what's happening here? So let's see. Let's build our nth term. Let's build our nth term. Okay? If this is 2 factorial, 4 factorial, 6 factorial, what is this one? What do you think?
8.
Not 1. 0 factorial. Got to go backwards. Okay? For my factorials, what am I adding every time? 2. So it needs to be what factorial?
2 and
2n factorial. Very good. Okay. I accidentally forgot, and I'm coming back to it now. Is it alternating?
Yes.
Yes. So I need a -1 to the n. The first term is 0. If I plug in a 0, I do get a positive. So did you notice that this one and cosines happen to be the same? The alternating doesn't change. So now, these are all powers of 2x. Do you agree with me? This is 2x to the first. This is 2x the quantity squared. This is 2x the quantity cubed, right? Okay, so we're going to write this as 2x to just the n, or do we need to adjust it? This is the 0 term. If I put a 0 here, is that what I want?
Two and
No, it's just n. Is it n plus 1?
This is 0, 1, 2, 3. Don't the terms match the
Yeah.
exponents? Yes. So that's it. We're done. There's the answer. Oh, no, it's not. Plus dot, dot, dot. All right. Let's look at the next one. Let's go to 6. This is e to the negative x. So which function on that list are we going to use? E to the x. So let's write down what e to the x is. How does it start?
1 plus x
1 plus x
plus x squared over 2 factorial.
plus x cubed over 3 factorial plus dot, dot, dot. There's that. So, what am I going to change my x's to?
Raise it at negative.
I'm going to make them negative. All my x's are now going to become negative x's. Okay? So now this function f of x is going to be 1 plus what? Negative x. I'm going to put it in parentheses, just to be safe. Plus negative x, the quantity squared. Make sure you put it into parentheses, because it does affect things, over 2 factorial. And then negative x cubed over 3 factorial plus dot, dot, dot. This is actually a rather easy one. So let's clean it up. So we have 1 minus x. What sign is the next term?
Minus.
Careful. A negative squared is positive.
Plus x
Squared over 2 factorial
minus x cubed over 3 factorial.
plus dot, dot, dot plus fraction bar. How does it differ from the original? It's just now alternating, isn't it?
Yeah.
Okay, so let's put the alternator on it. -1 to the n, is that correct? If we start at 0?
Yeah.
Yes, start at 0. So that's right. And then you can use the pattern for e to the x after that, which happens to be x to the n over n factorial. Just copied it off the chart. 0, 1, 2, 3 for x's. Factorial number's the same on the bottom. Okay, is it getting a little easier? A little bit? Okay. We're going to stop with number 7 today. We're going to do number 7, then we're going to stop. So f of x, hold on a minute. Here's the difference with this one. Notice there's 2 things that are multiplied. This isn't an inner-outer kind of a thing like we've been doing to now. It's x squared times the e to the x series. So what we're going to do is we're going to just copy the x squared down, open a parentheses, and write down the e to the x series. E to the x goes 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus dot, dot, dot. Close your parentheses. Yes, ma'am?
Whenever you have 2 functions, like that one on the bottom, x cosine, do you always put the one that's cosine, you do that series, and leave the x outside?
Yes.
Okay.
Yes. If it's a multiplied function, you leave it outside. If it's an inner function, you put it in. That's the difference. Okay, now I want you to distribute and see what the pattern's going to be. So f of x is equal to, what's the first term?
X squared
X squared. What's the next term? X cubed. What's the next term?
plus x to the 4th
X over 2 factorial. So the only thing that's changing is the x on top, right? Then x to the 5th over 3 factorial plus dot, dot, dot plus blank. Now it's time to figure out the last term. It is not alternating this time. Okay, let's give our denominators. Can we go backwards and make the denominators work? If this is 3 and this is 2, can I put 1 right there?
Yeah.
Can I put 0 right here? I sure can. Okay, that's going to help. So if we start at 0, and I want you to start at 0 as often as possible, the bottom is going to be what? N factorial, exactly. Now the top is a little different.
Is it n plus 2?
N plus 1.
Okay, how much am I adding for each exponent? 1. So it's 1n for sure. And then plus how much if I plugged in 0 first?
2.
It would be 2. That's the answer. Plus dot dot dot. Tomorrow we will continue practicing on this, and then we're going to take it down a different road, show you some more application kinds of problems. So now we've talked about multiplying, we've talked about doing a chain rule, kind of a composition thing, and we've also done derivatives and integrals. So that's it for today.